We've seen now how regularization can play a role in logistic regression to find much better fits of data and better estimates of probability. Let's finally talk about how we can learn them from data, those coefficients, using gradient ascent. And it's just going to be a very, very tiny change on what we did for learning the coefficients in logistic regression. So with like a tiny change to your code, we now alleviate all those overfitting problems that you had before. So again, same setting as before, training data, features, same model. Now we have L2 regularized logistic regression or log likelihood as our quality metric, and we're going to talk about the machine learning algorithm to address it, to optimize it, to get W hat. We're going to be using the same kind of gradient ascent algorithm that we used before, where we start from some point and we take these little steps, little eta steps, until we get to our solution W hat. And the same kind of approach where we're taking the old coefficients, adding eta times the gradient, and getting the new coefficients Wt plus 1. And so the only thing that we have to ask ourselves is, what is the gradient equal to now that we've added this extra regularization term? So we somehow need the gradient of the regularized log likelihood. Let's see what that looks like. We've seen that our total quality is the sum of the log likelihood of the data, which is a measure of a fit, minus lambda times our regularization penalty, which is this L2 norm squared. And so what is the derivative of this thing? This is the thing that we need to be able to walk into that hill climbing direction. So the derivative of the sum is the sum of the derivatives. So the total derivative is the derivative of the first term, derivative of the log likelihood, which thankfully we've seen in the previous module, minus lambda times the derivative of the quadratic term here. And it turns out the derivative of the quadratic term we already covered in the regression course. But we're going to do a quick review here. But as you can see, just a small change to your code before, we just have to add this lambda times the derivative of the quadratic term. So as a review, the derivative of the log likelihood is going to be the sum of my data points of the difference between this indicator, whether it's a positive example, and our probability of it being positive, weighed by the value of the feature. And we talked about last module and interpreted this piece in quite a bit of detail, so we're not going to go over it again. We're going to focus on the second part, which is the derivative of that L2 penalty. So in other words, what's the partial derivative with respect to some parameter Wj of W0 squared plus W1 squared plus W2 squared plus da 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 plus Wj squared plus da 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 plus Wd squared. Now if you look at all of these terms, W0 squared, W1 squared, all those don't play any role in the derivative. The only thing that plays a role is Wj squared. And what's the derivative of Wj squared? It's just 2Wj. So that's always going to change in our code. It's actually 2Wj. So in fact, our total derivative is going to be the same derivative that we've implemented in the past, minus 2 lambda times Wj. So 2 times the regularization coefficient, the regularization penalty, the parameter lambda, times the magnitude, so times the value of that coefficient. So let's interpret what this extra term does for us. So what does the minus 2 lambda Wj do to the derivative? So if Wj is positive, this minus lambda Wj is a negative term, negative contribution to our derivative, which means that it decreases Wj, because you're going to add some negative term to it. It was positive, you're going to decrease it. So since it was positive and you're decreasing it, what happens is Wj becomes closer to 0. So if Wj is positive, you add a negative number, it becomes less positive, closer to 0. And in fact, if lambda is bigger then that thing becomes more negative and it's going to zero faster. That's what happens. And if Wj is very positive, that the decrement is also larger, so it becomes, again, goes towards zero even faster. Now, if Wj is negative, then minus 2 lambda Wj is going to be greater than 0 because lambda is also greater than 0. And what impact does that have? So you're adding something positive, so you're increasing Wj, which implies that Wj becomes, again, closer to 0. It was negative, I added a positive number to it, it goes a little closer to 0. So this is extremely intuitive. The regularization takes positive coefficients and decreases them a little bit, negative coefficients and increases them a little bit. So it tries to push coefficients to 0. That's what effects it has on the gradient. Exactly what you expect. Finally, this is exactly the code that we described in the last module to learn the coefficients of a logistic regression model. You start with some w is equal to 0 or some other randomly initiated or some kind of smartly initiated parameters, and you go, for each iteration, you go coefficient by coefficient, you compute a partial derivative, which is this really long term here, sum over data points, the coefficient, the feature value times the difference between what is a positive data point and the predicted value of positive. So we call that partial j. And you have the same update. Wj at t plus 1 is Wj at t plus the step size that multiplies the partial derivative just as before, which is the derivative of the likelihood function with respect to Wj. And all you need to change in your code, there's only one little thing to change in the code. You add this little thing here, which is our only change. In other words, take whatever code you have before, put minus 2 lambda Wj in the computation of the derivative, and now you have a solver for L2 regularized logistic regression. And this is going to help you a tremendous amount in practice.